Welcome to another episode of Robo Papers. Today, we're super happy to have Siyuan and Yixuan, authors from the paper Clone, Closed Loop Whole Body Humanoid Teleoperation for Long Horizon Tasks. Thank you so much for showing up to share your work. Maybe as a start, if both of you can talk a little bit about yourself, how do you get into this research in the first place? That would be great.
Okay, thank you, Michael and Chris, for inviting us. And I'm Siyuan Huang. I'm currently a research scientist at Beijing Institute for General Artificial Intelligence, aka the Big AI. And I think we have been doing the humanoid research for like 2 years. And during the last year, actually, we established a joint lab with Unitree. So we are trying to collaborate to adjust the high-level planning or control things stuff based on the hardware they have been building. And I think the company of Unitree, they are pretty good at building hardware and the control system. And for us, we have been developing algorithms for the interaction, teaching the models to how to interact with the 3D thing and how to understand and grounding certain concepts in 3D thing. So actually, we are trying to build more advanced system to recognize the environment and to interact with the 3D thing with our joint technology. And I think today we have Yixuan with us.
Hello, I'm
there's a lot of
Yixuan.
feedback.
I'm currently a second-year PhD student at Beijing Institute of Technology, and now I'm a student intern advised by Siyuan at Beijing Big AI.
Okay, well, good to have you, Yixuan.
Yeah, so today I'm actually want to share one of our papers called Clone. And so here is a very short slide summarizing the content of the papers. So basically, we are trying to build a system for the general humanoid teleoperation and control. And Clone is one of the papers that representing a very good teleoperation system so that we can use the closed loop technology, you can use the localization and vision technology for the consistency between the operator and also the robot. And here is a very short background about myself. So I graduated from UCLA at 2021, and then I have been working as a research scientist at Big AI for 4 years. My research topic has been the 3D understanding for the general purpose agents and also the robots. So nowadays we have seen a lot of humanoid system, or we can call them generalist robot. So basically we have some definition for the generalist robot, not just for the hardware and also for the software, how the robot can really interact and do the decision making autonomously. I think autonomous is one of the big difference between the current robot and the future generalist robot, right? And we have seen a lot of demos from different companies like Unitree and Boston Dynamics. Did some preview of really awesome local motions, like the Kung Fu in the left side, and also some very challenging local motions like kneeling down and crawl on the ground from the Boston Dynamics. And after seeing all kind of these demos, our question is, are this robot really generalist robot? And how far are we from this kind of generalist robot? So by reviewing the current papers and also technologies, we have seen most of these robot demos, they are about locomotions and they have limited interactions with the 3D thing. From the top left side, we have seen this is the most recent boxing videos from the Unitree, right? And actually we have talked with their people recently. So basically the scheme or the underlying technology is that they have distilled different kind of actions, certain actions like punch and avoid, this kind of actions using specific command. And then you can see there's one people, they are controlling the command so they can control the robot in different actions. So the two players can play against each other. So we can see this kind of action, local motions and interactions, most of them are pre-programmed. And then you can control your command and you can control the robot. This demo have been already really impressive, and I like the boxing a lot. But the problem is that they don't have very sufficient and accurate interaction with the 3D environment. So in the future, if we want our robot to really come into our home and help us to do some daily activities, we want them to have better interactive capabilities with humans, with the environment. Right? So by seeing these two videos, we can find out that humans can do a lot of stuff in our rooms, like they can pick up objects, they can squat, they can operating in different heights. Currently, we have seen demos from robots. They're doing a lot of impressive like tabletop manipulation. But basically, they are all operating in the same like height. If you are changing different height, increasing the operation space, like most of the robots, they cannot do very good activities in different height of level, like picking objects from the ground. This kind of tasks are very difficult for the current humanoid robot. And so inspired by this kind of very diverse activities from humans, we are thinking about, can we like build humanoid robots just like the activities and also the capacities of the daily humans? So we can pick up the object from the ground, we can squat, and we can bend our like elbows and this kind of very rich activities. So this is the original motivations of our work. We want our robot to have the same capabilities of human interactions in our rooms. And in order to achieve this kind of capabilities, actually we have the most efficient way is to learn some capabilities from the videos, right? Or from the demonstrations. And I have seen one of the slides from Chris. It's very inspiring. It's about comparing the data that is, or the demonstrations that are used in the foundation model and also the robot learning, right? So from the left side, we can see like you have like 1 billion hours demonstrations for the large foundation model like GPT or Chenwen. It's kind of visual language foundation models. And for the robot policy, I think the current situation is that we don't have enough data, but for the tabletop manipulation or even the cross-embodiment manipulation, we have like for the Pi Zero policy, they have collected like 10,000 hours of demonstrations for learning this kind of multi or cross-embodiment policies. And for the humanoid robot, for the recent Groot robot from the NVIDIA, they have like 88 hours from the like upper body interaction demos. However, I think the problem we mentioned is about the whole body interactions, right? You can interact in different rooms, in different operates in different heights. I think this kind of whole body interaction data is still like, we don't have this kind of data. So it's about like, I would say 0 hours. If I'm wrong, you can correct me. I think currently we don't have enough data for this kind of really high fidelities and high degree of freedom interactive data for the humanoid robot, for the bipedal humanoid robot. So if we don't have the data, it's hard for us to really learn the policies. So the first question that comes into my mind is like, we really need to build a good system to collect such kind of whole body interactive or interaction data for our daily activities. So this is why we want to do this project and why we want to achieving such kind of capabilities for the humanoid robot. So I think one of the challenges for facilitating such kind of human motions or control is that training an expressive humanoid controller is really hard. So basically with the high freedom we have, so for current G1 robot, right, we have 29 degree of freedom. So that will result in a large and complex control space. And if we want to derive in such kind of human-like expressive motions, we need some human priors. So the bottom right demo is a locomotion policy that we are training without any human priors. So we can see the like walking style is kind of not really human-like. So if you are trying to building this kind of human-like interactions, we really need to leverage those kind of human motions for us to learn. And I think that...
Sorry, one question. So you just as a comparison, so you mentioned H1 has 29 degree of freedom, and this is without the hands, right? This is just up to the wrist, I suppose.
So the G1 has 29 degree of freedom. Actually, the H1 I think they have.
Oh, sorry, G1 has 29.
Yes.
A human would have how many, like, degree of freedom? If you were to do a comparison.
I think a human may have like, you mean all the motors for the human, with
Yeah.
also including the hands?
Mhm.
I think for humans, for each hand, you have like more than 20 of degree of freedoms. And for the arms, we may have like 10 degree of freedom each arms. I think probably we have more, like 100 degree of freedom, more than 100 degree of freedom control for the humans. Like, for example, if you want to really model that is not like includes the muscles and this kind of mechanisms behind the bones of our human bodies. So basically we have more than 100 like degree of freedom compared with the current humanoid robot. But I think 29 for the G1 is relative already a lot of like higher than the current bimanual manipulation. For the bimanual settings, we have 7 degree of freedom for each arm. So basically they are about 14 degree of freedoms for the current, like the main trend of the bimanual manipulations.
Okay.
And we think that we need to leverage some human motion prior for the humanoid control. And here is a typical process of how we transfer this kind of humanoid prior or the motion prior into the like humanoid robot learning. So first we have some motion capture data. So this kind of data is very useful in computer vision tasks. So basically you have like the multi-view cameras, and you use the cameras to capture certain kind of actors. They are acting in this 3D scene, and they might have certain interactions with the objects, with the furnitures, and the small objects, place the objects, and also grab something. This kind of interaction activities. And then the next step is people are trying to do the retargeting. So they can retargeting from different degree of freedoms, just like we mentioned before. For humans, we have richer like complexities, and we want to retarget them, this kind of motions. For example, the simple parameters or the simple motions into the robot, like the G1 robot. And then we're trying to use them to learn the policies or trying to help the control policies. And after that, we can design a humanoid controller. So that can be MLP, can be a measure of expert policy, can be transformer, and maybe some more native PID or MPC controller. And after that, we can leverage this kind of human motions as like tracking reward and using and such like additional rewards for the controller. And then we can have some human-like behavior. Like this kind of squad is learning from the human motions because they have been learning how to track the squad motions. And after training with RL policies, with RL algorithms, they can learn such actions in the simulators and transfer them to the real world. I think this is a typical process of how we deriving such human-like motions to the real world robotics or to the humanoid robot. So, like after seeing all this kind of controller and teleoperation system, we have found there are some challenges for the really whole body teleoperations and for the long horizon humanoid task. And the first challenge we have found out is the current system, they are trying to do a lot of open loop teleoperations. So basically, if you are trying to teleop the robot in the local coordinates and trying to retarget the motions from humans to robot in local coordinates, then the global tracking might be very ineffective. There are some severe tracking error accumulations along the process. So as long as the teleoperation process has been continuous, like 1 minute, or you have like 15 meters of translations for the tasks, then the accumulated error might be very large because all the things you're trying to do is to check the local motor or the local coordinates of between the operators and also the robot. And the second problem we have been seeing is that people are tending to use a separate policy for controlling the upper body and lower body. And I think in certain situations, this kind of separate control is pretty good. For example, you can stabilize your lower body, and you can operate, or you can have exoskeletons for controlling the upper body. So for achieving tasks like the tabletop manipulation, you can have like very decent performance with this kind of systems. However, when you are trying to have more coordinated motions, like you are bending your, or you want to crawl on the ground, this kind of more dynamic teleoperations or more dynamic tasks, this kind of separate control policy might be not enough for this kind of task. So we are thinking about, can we like unlock the full potential of the upper and lower bodies and combine the control of the upper and lower bodies, just like humans. So then we can have more capacities for modeling like more challenging tasks and more similar to the capability of human interactions in the 3D room. And the third challenges we have observed is that, so currently we are trying to learn the motions from the human motion dataset, like I have shown before. So basically we have like two mainstream datasets. The first is called AMAS. So basically it's a collection of the motion capture data along different computer vision tasks. And the second is the LeFan dataset. That is for the gaming industry and the gaming applications. So this kind of two datasets, they have limitations in the like whole body. They don't have very expressiveness of the whole body interactions, and we have check all this kind of data, and they can also support very like high level of degree of freedom for the real whole body interactions. So these are some challenges we have observed. And for the first challenge is like for the open loop control, as we can see that if we are just control the local coordinates and the joint change position, there will be like accumulated of the errors. And here is a demonstration. So for example, if you are looking at the teleoperators trajectory, like the green one, then if you don't have a global consistency, if you are not trying to correct the global position of the operator and the robot, then the errors might accumulate. So the orange trajectory might not be very different, might not be exactly the same between the operator and the robot. So I think this is one of the main questions. Like imagine you are trying to do a very complex and long-term interactions in the 3D sim, and the operator want to collect some very high quality and accurate data, but the positional drift and the rotational drift will cause a lot of trouble if you are trying to collect this kind of long horizon data.
Do you have to do any correction for like accounting for the environment in that case? So like if you're trying to like, so you're just saying if you're doing some task in the environment picking up the objects, but like, so do you optimize for like the positions of the objects as well over the trajectory? How do you handle that?
I think the current solution is that we are calibrating the position of the operator. So we have Vision Pro system, and it can help us to have the localization for the operator. For the robot, actually we are using the odometry technologies. So we are using the LiDAR and also the IMU system on the G1 robot. Modeling the background and also the object, it can have the like real-time localizations, and this kind of information provides a global position.
So just the global pose of the entity is enough. You don't need to close the loop on the objects as well or anything like you're interacting with, I guess. That's
Yeah,
makes sense.
I think we don't have the close loop for object. That's much harder than the current setting.
Yes, that's very hard. Okay, it's good to hear that you don't need to.
Yeah, but maybe if we incorporate that, might be a like good technology or good thing for the thing without very clear background. For the white background, we actually want to check the object for a better localizations. I think that's a trade-off between the system or how you can do the localization and how you can do the SLAM, right?
Yeah, that makes sense.
And so this is the first challenge we have found out. And the second is the separate control of the upper and lower body policies, right? So basically we have seen systems like Homies from Shanghai AI Lab, and they have been designing a separating system for the upper body control and lower body control. So for the lower body control, they have a pedal, and they can have separate command for controlling the lower body like movement, like walking and squat and turning. And for the upper body, they have exoskeletons for more accurate upper body interactions. This kind of a separate control system is stable, but they will have troubles when you need some coordinations with both the upper and lower bodies, and for some outdoor, more dynamic interactions. For the interactions that human or robot are really specialized and are really good at, they are not very robust, or they are not very useful for this kind of dynamic interactions. And the third challenge is the underrepresentative dataset for humanoid training, and we'll show them later. So basically, for the left one is the AMS dataset. They have a lot of motion captured interactions. And right one is the LeFan dataset. Actually, we have seen a lot of humanoid dancing, like unitary demos. So they are actually learning from the LeFan dataset. So they are recording a long turns of motions from an actors, and they have dancing, like boxing. So we can using certain clips from the LeFan dataset and use them to learn the humanoid policies. So, but after trying this kind of two dataset, we have found out that the activities of the whole body, including the combination of the wrist and also the arm, and this kind of degree of freedom is not very good enough for the dataset in these two dataset. Yeah. And so basically, we summarize 3 challenges for current teleoperation system. And the next, we are trying to show some work of the clone. So basically, it's holistic closed-loop whole body teleoperation system for the long horizon humanoid task. So here is a short demos. So in this work, so basically, as we can see from the demos, actually we want to build a system so that the human operator can only use a single Vision Pro. So we have 3 points as the input. They can use the Vision Pro to control the humanoid robot in real time with the full degree of freedom of the G1 humanoid robot. That basically means 29 degree of freedom. So we have shown some like long horizon demos and also the boxing demos. And I think this philosophy is different from the boxing demos from the Unity themselves, because I think they're using the command and distilled actions for controlling the boxing robot. And for us, we are actually building up a real-time and interactive system. So for 2 players, they can actually do certain kind of actions, and the robot can play. And here shows some very dynamic interactive actions like squat and walking during the squat. And you can actually do a lot of wrist flip actions. So this unlocks the degree of freedom of the wrist. So datasets from the LeFan and AMS, they don't have this kind of very agile activities of the wrist rotating and also translating. And using clone, we can control robot to do some real-time sports tasks, including the boxing and also the table tennis.
Oh.
Here are some handover tasks. Yeah, and also we're trying to demonstrate that robot can do some warehouse, similar to warehouse tasks. Although the box is empty and pretty light, but I think this is a good demonstration. So currently, the lower body policy is not very stable because we are only using the 3 points as the input. So basically, lower policy, the legs, they're trying to imagine like how the legs should move according to the 3 points.
That's what I was going to ask. So what are the inputs? What is it?
So the input for these policies are just from the Vision Pro. So basically, you have 2 points from the hand and 1 point from the head pose. That is all the input for the system.
But the Unity G1 doesn't have like a mobile head. What do you use that input for? Just like the torso position?
and also the 3 fingers of human hand. So actually the
Got it.
vision probe are tracking the 3 fingers of human hand and also the location of the torso.
Cool.
And that's the demo of our work. So for the models, actually we are using a 2-stage training paradigm. So for the first stage, we're trying to train a teacher policy in the simulator, and we're using 2 rewards for the policy training. The first is the tracking reward. So the tracking reward is trying to imitating or tracking the human motions according to the reference motions. So for the motions like squat and different kind of dynamics, the policy is trying to following this kind of motions in the simulator. And the second reward is the AMP reward, the visceral motion prior. So basically this is trying to regularizing the lower body movement. So for the current system, the input is only 3 point. So for the lower body, like the legs, the body needs to like imagine the movement according to the 3 point. The visceral prior is trying to regularize the learning, so the model can have some motion human priors for the lower body, make the learning process easy. But in the future, if you are trying to like build more sophisticated motion capture or the input system, you can use a upper body tracking. For example, you can use a like exoskeleton, or you can have a motion capture system like the work twist is doing from Karen's group. You can use whole body human motion captures by adding the control point for the input observations. But actually the principle is quite similar. So basically we're trying to use fewer control point as we can to demonstrate the potential of the whole body tracking. So we are adding the AMP prior. But if you are using more points as a control input, you might not need the AMP prior. So this is the first stage for the teacher policy training. And I would say this stage is quite similar to some of the previous work, like the Omni H2O from. And the second stage is student policy distillation. So basically the purpose of the distillation is that during the real-world deployment, the input observation is partial, and we're trying to distill the teacher policy we have learned into a student policy. So that basically means that we have to have a like dagger-like process to do the distillation, to imitate the output for the models. And in our work, we're trying to using the mixture of expert policy to increase the robustness of the student policies. And we have found out that by adding this kind of MOE policies or MOE experts into the training, actually the real-world deployment has been much better than original student policy distillations. And we think that's related to the noises of the real-world experiments. So for the simulation-wise, we haven't observed very significant improvements, but for the real-world deployment, actually the difference is pretty significant compared with the policy that is not using the MOE distillations. So basically, the expert they can try to like learn the motions from each expert. They can learn the motions for different episodes or different sequences, and during the executions or during the inference time, the policies can choose to activate certain expert for certain kind of motions. And we have done some ablations in the following part to demonstrate that the MOE part can actually help the motion learning. And so, as we mentioned before, we developed the localization system for both the teleoperator and also the humanoid robot. And we're trying to make the teleoperation process like globally consistent between the operator and also the robot. And here is a comparison, and here, this is how we did it. So basically we have a tracking module for our MR device, the Vision Pro, and the Vision Pro can identify the global locations. And for the robot, we're actually using the LiDAR odometry. We are using the RGBD images and also the IMU and also the LiDAR system to have accurate and real-time localizations and also identify the rotations of the head movement. I think this kind of localizations can really help to improve the consistency between the human robot and the operator. Actually, if the human robot, they are not operating in a correct direction, they will also like correct this kind of errors in the next time steps or in the next frames of executions. And the lower part is a demonstration of how this kind of closed loop systems can help the teleoperation system. So the green trajectory is the policies or the system we are designing. So every time we have observed some global positional drift, we like identify, we can tell the policy, okay, there are some errors and you need to correct these errors. So the policy will try to correct this kind of global positional errors. So along the time, since I think the odometry, they run at 10 Hertz and the policy runs at 50 Hertz. So basically the localization and the actions, they are almost real time. So by real time, we can like correct this kind of positional drift. So along the way, even if you have very long trajectory, you're going a step out for 15 minutes, 15 meters, the errors will still remain pretty low according to our experiment.
So concretely, because like for example, in this case, the human controlling with a Vision Pro, he's a fair bit taller than, let's say, the G1. But let's say if he runs or walk for 50 meters, maybe it takes 50 steps. So am I right to assume that basically using this closed loop, using clone, somehow G1 will also reach the 50 meters, but in the meantime, it could have taken 60 steps because it's a smaller embodiment. In reality, is that what will happen?
It will step out like 50 meters. It might have more steps, like 20 or...
Okay.
Yeah, I think another advantage of this system is that if you are really trying to operate a robot in a very large distance, for example, to the extreme, if you're trying to control a robot on the moon or on the Mars, this will be pretty useful because you want to control the robot in a very accurate way. And so the absolute distance will be a very useful signals for have a accurate control. But in a room-like environment and also in a like room-like environment, if you have one versus one like replica of the 3D environment, that will also be very useful. By doing some experiments, we actually found out this kind of global operations will help us to do the household activities compared with like the policies that are not using the global localizations and this kind of consistency. And we also curate a dataset called the clone dataset. So it's a dataset for the expressive whole body interactions. So in this video, we show what we did by doing the data filtering, risk sampling, and motion editing. So the motivation is that the motions from the image, they don't have agilities in the wrist. So basically, the motions are basically like they are doing the dancing actions. But for the real-time control for daily tasks, we have very high demands for the degree of freedom over the wrist and over the combinational space of the arms and the upper bodies. So this is I think it's a missing piece of the current motion dataset. So we are trying to use our mocap system, motion capture system, to overcome this kind of challenges. So by creating this kind of mocap data, and we can do some risk sampling, we can have more augmented motion captures, we can do some motion editing, so we have more combinational space or combinational motions of the upper body and lower body movement. And like these demos, here is the mocap system. Because we are trying to make the humanoid movement as like humans as possible. So the operator in the mocap system, they're trying to do different kind of actions while fixing the lower bodies and enrich the activities of the wrist and also the to like upper arm.
Why are you fixing the lower body?
Because for a lot of manipulation tasks, the fixing the lower body will make the actions more robust.
Fair enough. Okay.
And here are some experiments. So the first experiment is trying to figure out if we are extending the horizon of the actions. If the robot or the operator, they are stepping out in a far distance, how large is the errors of the humanoid robot? And here we're trying different distance of human movement. For example, like 3 meters, 6 meters, and 9 meters. And the results shows that although the distance might be different and might be long horizon, the error is relatively the same because basically our system provides a global consistency between the robot and also the operators. As long as the localization is accurate.
It's actually pretty low latency, honestly, as well. It looks like.
Yeah. I think
did you guys?
Yeah. Oh, sorry. What's the question?
Did you guys have to work pretty hard to get that? Like, it's very responsive, I would think.
Currently, we have an internet cable, and I think we have optimizing the speed of the localization process. We are using the fast Leo to do the localizations, and for the policy, we are also trying to make the policy as simple as possible. Currently, we're using the 3 layers of MLP with several mixture of experts. So there is not a lot of too much computation along with the policy itself. So this makes the latency relatively slow.
That makes sense. That's actually a very small policy, much smaller than I was expecting. Okay.
Yeah,
cool.
yeah. We have some works like dealing with or trying different like transformer or diffusion models, this kind of policies, but the efficiency becomes a huge problem because we want the policy can run in a real-time way.
So you found like the mixture of experts was enough to really to have enough capacity to get all the right behaviors without like basically the size that would come from a transformer.
Yeah, I think it's a compensation for the expressiveness of the MLP models. So basically, if you have transformer, you have more capacities, right? You can model more expressiveness in the dataset. I think the MOE also adding some more parameters into the model so they can handle more expressiveness in the motion dataset.
But because it's an MOE, you don't actually need to evaluate all those parameters. So then it can still be very fast, I guess.
Yeah, still pretty fast.
Yeah, cool. That's actually really, really interesting. Thanks.
And we compare with we did some ablation. And the first is about how the mixture of expert and also the dataset can really help the motion tracking performance. So by comparing with the model that using the MOE and not using the MOE, we have found out that tracking errors has been made pretty low compared with the model that are not using the MOE. And I think this showed the mixture of expert can actually improve the tracking policies in the simulators and also the robustness in the real-world experiment. And the second is our policy really manage this kind of diverse motions using one single policies. I think this is kind of advantage we want to have, or this is kind of policy we want to have in the future. And compared to the current, a lot of demos from industries that are using the multiple policies for different motions. I think one policy can really benefit the future teleoperation system and help us to create some high quality and very accurate interactive demos.
Yeah, the bottom right one was very cool. Even like you have someone pushing the bot away, the robot the policy was still, okay, because of the tracking reward, I suppose, like want to go back to where,
this one, right?
Where it's supposed to be. Yeah, the bottom one, yeah.
Yeah, I think it shows the advantage of the localization and the global tracking, right?
Yes. Yeah.
If you're trying to push in the robot, it will come back immediately.
Yeah.
Yeah. So I was watching the one in the lower left to try to finish the circle after the guy stopped, which I guess is the same thing. It's also the closed loop tracking, right? Like That's.
I also find that the squatting is very impressive because like ultimately you're just tracking the hands and I think the head, right? But and yet it's able to infer that if you are going down, likely your lower body need to squat. So must have learned all this during the teacher and and then to student policy. So somehow is internalized all that. I mean, there are different ways to squat down, right? You can squat down with, let's say, like a knee up and then a knee down, but then but still at least you get the upper body down. And I think it's anyway, really impressive.
Yeah.
Okay.
Yeah.
Sorry
Yeah.
to interject.
I think this is a very good comment. Basically, the squatting, you have different gestures for the squatting, right?
Mhm.
And we have like Asian squat, this kind of action.
Yeah, exactly. Asian squat versus
Yeah. So basically, the model is trying to imagine the lower body actions according to the 3-point. And I think basically during the squatting process, the model saw the 2 points, the hand are really low. So they're trying to lower down the lower body to tracking the 2 points from the human hand, right? I think the problem of this kind of 3-point control is there's certain ambiguities for the lower bodies. You can see a little bit like adjustment or movement of the lower body. They are not very stable. I think it's also due to the same principles, because I try to imagine the lower bodies wherever the imagination is different or it has some stochastic output. The lower body will try to adjust, and that will not be very, very stable compared with like the motion capture input. You have full body key points as the input. And I think we're trying to explore the advantage and also the drawbacks of these two systems. Maybe try to combine their advantages in the future. And we did some ablations by using only the AMAS data and the data set we are collecting. And here the learning curve or the error bar actually showing that the model using the clone data set has actually achieving a better convergence performance and a better tracking policy, especially for the upper body with the wrist and also the arms.
Sorry, so I have a question about the data set. So the curated data set you mentioned, like in relation, let's say, to AMAS and Lafont, like what are the different sizes and like versus yours? Like how much more did you augment those to those?
I think you mean how much we have collecting or how much we are using.
Oh, collecting. Like in this new data set, I think it's called CloneNet, right? I think.
Yeah. So basically, during training, we're using 130 sequences from the AMAS, and we collected 20 or so motions by ourselves by augmenting or checking and enlarging the action space of the upper body. So basically, as we're saying, it's a compensation or to we identify the drawbacks of the current data set and focus on this kind of underrepresentative motions. We collected 20 sequences for this kind of actions.
So 130 plus 20, so only 150 total? Sorry, Michael.
Yeah, sorry. Similar question. Yeah.
Yeah, only 150. We augment them this kind of motion, so they have about 300 or so. But original motions for the AMAS plus our clone D is about 150 sequences.
And those augmentations though were mostly targeted like the wrist motions, and it's not like it's doing something fundamentally different like the rest of the body, I guess.
Yeah. Most of them are retargeting and a little bit editing. Basically combining different action spaces of the upper body and lower body.
I see. So would you have an arm, one arm motion from one behavior versus one to another, or do you mean temporally sequenced, do one thing then the next, I guess?
Can you repeat the question? The internet is not quite well.
Yeah, sorry. So when you're talking about combining them, are you talking about combining them sequentially, or combining one set of joints from one motion and then another set of with another one? So maybe the arms from dancing with the legs from running. I don't know. What do you mean? I guess
I think currently we're just combining all of them into the training process in a very intuitive way. Okay. Just combine them all as one data set and then learn the motions.
Yeah.
And each of this sequence could be quite short, right? I imagine. Let's say out of this 20 sequence, could you give one concrete example? I'm just imagining, is it one sequence just rotating the wrist and that's considered one sequence? Is it something like this?
I think I'm not sure whether this is a whole sequence. Yixuan, can you elaborate more? Is this a whole sequence of the motions?
No, it's just a part of it.
Like how long is each sequences for our own like capture the motion capture data? How many seconds it have?
It's about
It's about 1 minute.
Okay. For each sequence we have like 1 minute total length for them. So basically the humans are doing different kind of actions in the
I see.
motion capture data set.
I see. So
I'm really
actually, it's
surprised.
just about 20 minutes to half an hour, like add together.
Yeah, I would say that.
Yeah. It's like at most like one morning's work.
Right.
Yeah.
I think
Could
the
you
student
talk
has been-
about how that's enough? How is that like we were just like you had the slide earlier with the 1 billion hours worth of data for GPT, right? Like why is 20 minutes enough here?
Yeah, I think it's a very interesting question. I think there's two different strategies and principles for the GPT part, and in this part, let me navigate to the previous slides. So I think this slide shows the data we need for learning, and especially for learning the visual motor policies. For the
Sorry, are
policy-
you sharing a screen?
Okay, I'm not
Yeah.
sure.
I think you stopped sharing for a bit.
Is it sharing?
Yep.
Okay.
Yeah, it's
I think for this part, we are actually we need a lot of data for learning the policies, right? Like the vision motor policies. So for the type 0 examples and for the group examples, they have pair data with the vision and also the actions. So they can train visual motor policies or VLA data. So our teleoperation system is actually trying to help us collect this kind of whole body data. And the data set we use, like the AMS and also the CloneD, is to train the teleoperation system. So that's two different objectives. And for the teleoperation system, like the AMS dataset, they already have like, for example, we use 130 sequences, just like 2 or 3 hours motion capture system. That basically means for humans, we are doing ourselves like local motions, like you can dance, you can do a different kind of actions. 2 or 3 hours might be enough. But if you are trying to put the humans in a more complex 3D things, and you are trying to that the humans can do certain kind of interactions, that demands a lot of larger, more data set. As we mentioned before, you need more data for Pi 0 or for the multimodal foundation models. So this is the data for training the teleoperation policies, but not exactly like the VLA training.
So that would mean, like, in your opinion, that maybe 2 or 3 hours is roughly enough to cover the space of different motions you might need to make, but not enough to ground those to useful actions and tasks and behaviors. Is that like with perception?
Yes. Yeah. I think the teleoperation system is trying to is like a bridge, like bridging the locomotion policy and also the interactive policies, because you need this kind of teleoperation policies to control the robot. And then with the human operators, we can use them to collect more and more, like 1,000 hours of interactive data set with the images as input.
Makes sense.
And for the multimodal model training or the policy training, actually we need to handle the generalizability problem for the scene generalizability, for the task generalizability, for the like image domain generalizability. So they need to counter this kind of generalizability. So they need a lot of data for the scaling, for handling different background, different 3D scene, and different kind of objects. Yeah, I think I want to mention one more. I think the bullet point for such kind of policy is that, so we are still in a debate between the wheel robot and also the like humanoid robot, right? We're trying to answer like why we need a humanoid robot. This is not useful. In a factory, in a home, it's not very useful. But I think a huge difference between the current technologies of wheel robot and humanoid robot is that the wheel robot, it can operate in different height. So basically it can operate on the table, and also it can lower the operation space into different, like open the cabinet and picking up the object from the ground using a very smooth like hardware design. But for the currently most of the humanoid robot, they cannot operate in different heights. So I think this will bring a huge gap between the current wheel robot and humanoid robot technologies. But with systems like a clone and also some current work like the twist, I think you have already did a podcast with them, right? We can actually control the humanoid robot in different height. So this can really unlock the potential of the humanoid robot and improving the generalizability. And the current system, although they might seem not very stable as we are expecting from a very functional robot, we're trying to improve this kind of stabilities. And we are also collaborating with the hardware companies like Unitree. They're trying to help us to improve this kind of teleoperation policies, especially for the robustness. As we can increase the robustness and increasing the functional spaces, I think they can reach similar capability of the wheel robot. At the same time, it has generalizability for different terrains like stairs. You can do the outdoor and the indoor tasks with better generalizabilities. So, I mean, in the future, we will see a very interesting chance for whether we are using trying to using the human robot or the wheel robot.
Yeah, I like the point about it being able to use its whole body and be able to crouch down and manipulate things at different heights. Humanoids should be better at that, right? Like picking up objects is another thing I would hope that they'd be better at. But so do you think clone will work for going upstairs as it is, or does it need to change in any particular way?
We are trying to develop a terrain flexible policies with clone policies, because if we are going to some environment like warehouse, there might be some stairs and terrains. So if the policies can really counter this kind of terrains, it will be much more useful.
So with that, I assume that would mean getting stair trajectory data or something from humans.
Simple way.
Yeah, that kind of stuff. Okay.
Yeah, I guess I have a quick question about with clone, right? How about when have you guys tried doing tasks that require pretty much higher torque or force? So for example, opening up a heavy door.
Mm-hmm.
I mean, recently we just did an episode with the author of Falcon, I think, and they have this kind of dual agent, dual RL thing, and I think the main takeaway I got from that was that it's very robust to, let's say, force, external force. But I also saw the demo where you have this guy pushing around, which is more sudden, So I wonder if you have tried tasks that, for example, lifting slightly heavier stuff, and then yet is able to track very close. Have you guys tried that?
So actually for the current policy, we haven't tried really large or really dynamic interactions. I think the main obstacle is the current hardware design for the G1 robot. So basically the motor for the shoulder and for the elbow, they are not very
overheat.
Overheat in an easy way and operate. If you are operating the robot in 10 or 15 minutes in a row, then it will have very severe overheat issues.
Got it.
But I don't see a technical challenge here. So basically for the policies, as we can do very fragile and real-time teleoperations, and this kind of interactions would be possible. And we can also integrate the tactile feedback onto the robot hand, right? We can have some tactile feedback and haptic feedback for the operators. Then in this sense, we can have more accurate or real-time responsive reactions for the operators, so they can react according to the robot interactions.
Yeah. Yeah, I think it's a big unlock, So there's a bunch of works that's coming out literally like yours, which is very impressive, by the way, that I think it's solving a very big UX bottleneck. So clearly the hardware can do it, It's just like you said, squatting down, just operate at different height. But if there's no easy way for the human to teleop in real world, then you can't even get the data flywheel going, right? You still, like you said, the whole body data set is still stuck at 0. But I think once you have something like that, and I'm sure there will be improvement, there will be a clone tool maybe later on, that improve, like you say, more terrain, robust to different terrain, go upstairs and, maybe go, sit down on a chair, that sort of stuff.
Yeah.
And all this would just allow it to be, allow for the human teleoperator to do a lot more. Yeah.
Yeah. And
very cool.
Yeah, we are also currently building some real world collection system. So basically in the demos, we show some examples, and these examples might not be very robust and might fail, but actually we are building some real world systems in a warehouse or in a real families. We're trying to test the generalizabilities or the stabilities of these really real applications. Yeah. I think we have some future release for this kind of real applications. Then is force feedback. You need to like lifting a heavy object and what is the issues, and we provide some feedback for the hardware companies so we can improve the like policies and also the hardware together. And I think they will be useful for the real downstream tasks in the future for the industry.
Are you also collecting a bunch of data out of this and try to train some autonomous policies, or is that not yet?
We are doing this, yeah.
Okay.
But we have some preliminary findings. So doing the upper body or training the upper body models is kind of like easy or kind of like
Understood.
yeah, pretty good for the upper body interactions. But for lower body, we are still trying, because for the lower body part, the dynamics is much richer and it need to do the balancing for the whole body, especially when you have holding certain objects and had heavy lifting. So the balancing is challenging for the entire model training, for the policy training. And I think we haven't seen any autonomous policies for a real whole body interactive policies. Even for the figures, I think they have like upper body interactions. That's pretty impressive, but I think it doesn't involve the lower body dynamics for the autonomous policies. Right?
I believe so. Yeah, I think those are all upper body.
I do have a question about your choice to use Apple Vision Pro.
Mm-hmm.
I suppose you may have tried using something like, let's say, a much cheaper VR device like a Quest 3.
Mm-hmm.
Have you guys tried that? And why Apple Vision Pro?
So the current advantage of Vision Pro is the localization capabilities, and also the human pose tracking capability is pretty robust on the Vision Pro. And for this project, we want to demonstrate a very generalizable teleoperation policies. So that basically means for the operators, you can stay at your home, you can at a school, so you can have different. So one of our things is at Peking University and at a park. So in different, like in the wild settings, you want to use the mixture MR devices, and they can provide some robust localization and also the hand tracking policies. I think we try different headsets. The Vision Pro did the most by far. Yeah, did the best by far.
And I'm trying to imagine like what it's like for the human teleoperator. I mean, I understand basically, I mean, Apple Vision Pro help with maybe, like you say, way more accurate, let's say, hand pose estimation.
Mm-hmm.
But is there a real need for the teleoperator to look also through the device? Like, can't he just put it on here and then just do it that way?
I think this is a very good question. It's definitely needed, especially during the manipulation task. So basically, during the manipulation, we are trying to do very accurate manipulative task. The third-person view cannot help a lot. And for dynamic tasks, the third-person view might do very good. But if you are trying to do certain first-person view interaction, especially for the manipulation, like picking up an object, if you have first-person view from the Vision Pro, that will help a lot of the efficiency of the teleoperation. Otherwise, the operator might fails again, and maybe cannot operate in a very like real-time way.
Yeah, I'm trying to think, because like, let's say I'm doing a desktop manipulation, maybe stacking up some Lego, and you have the G1 and then you have the human teleoperator. So I'm just trying to think because like, I mean, I've used a lot of this, like I've got Apple Vision Pro, I still get headache after a while, you know?
Yeah.
So especially I imagine there's, clearly there's still latency, even though it, as impressive as your closed loop, right? There is still, it's not even latency. It's not latency from, it takes a while before like the policy catches up, right? I mean, maybe it takes 2 steps for a G1 instead of 1 step for a bigger human, right? Let's say. So there's already there's latency via different sources. So I'm trying to think, wouldn't it be easier if I just like, if the teleoperator take it out and then the teleoperator look at what the G1 is doing and it's right next to it. But what your point is that it's actually still better to kind of force the human teleoperator to look through from the perspective of the G1.
I think the problem you mentioned is very like realistic, because for the current settings, the operator needs to train. We need to train the operator.
Yeah, I'm quite amazed that he didn't fall down himself. Like, because what he's seeing is like 1-2 seconds behind, Once he turned, like, he doesn't turn, like,
Yeah, actually, we really need to train the operators. And in the future, we think there's plenty of jobs opportunities for this kind of operating tasks.
You're used to a slightly delayed version of the world, basically.
Yeah, you need to get used to the
Um,
delay. But technically wise, I think for certain tasks, you can like just take off the Vision Pro and look at how the G1 is doing on certain tasks. But for very manipulative wise, if you are trying to manipulate really small objects, so you need to control the fingers in a very accurate way, I don't think a third person will helps a lot. And maybe the efficiency might be pretty low compared with you have a first person view teleoperation. Yeah, I think that's the main challenges because if you want to go down to the applications, the first application and the most important is the manipulation, right? But if you are not doing a very high efficient, very efficient teleoperation, that will be like a pity for this kind of teleoperation system, I would say.
Okay, got it. So basically force the human to adapt. Yeah.
I mean, we
Yeah,
try
fair
to
enough.
improve the system,
Yeah.
making the lagging like less
Yeah.
compared with current system, right?
Got it.
Reduce the
Yeah.
lagging.
All right. Yeah. Anyway, I mean, congrats on the work. I thought it was very, very impressive. Honestly,
you.
like,
Yeah,
and
absolutely.
yeah, it's quite amazing to me that you just effectively have three, points that you're tracking and then infer the whole body. So yeah. Yeah, I guess is there, I mean, you already mentioned a couple of things that you guys are kind of thinking of working on, like, making it more robust to different terrain, maybe training autonomous policy based on some of these data set that you guys are but yeah, I'll say just maybe on the teleoperation side, like besides the terrain, what would be some other like improvement if you guys were to do a clone 2 that you love to like build into clone 2 as well?
I think for the teleoperation system, like in a very practical way. So in certain settings, we don't need the very accurate global consistencies. So we are trying to making the control method be diverse. For example, we can choose to separate upper and lower body policies, and we can choose to combine the upper and lower body policies, and we can switch between the global tracking and also the local trackings. So for certain circumstances, if the humans or the operators want to switch their operation choices, they can switch in our settings. That will be useful for different applications. And I think this is one of the design actually we are trying to build in our current system. And I think the second one is the model-wise, because currently we're using a very simple model choices, MLP layers with several MOE, but actually the expressiveness and robustness might related to the capacity of the models. So we're trying to enlarge and empower the models to try whether we like using the transformer or diffusion model, stability will increase. Yeah, I think these two directions. And the third one is we're trying to try more dynamic tasks like jumping or doing some kind of sports. As we showed some demos like doing the
Table
boxing
tennis.
and the table tennis. You need some instant feedback. But how about other activities? How about other sports? Like
I think it'd be crazy if you can play football even though you're just tracking the hands. I think that would be crazy. Like just infer how to kick a ball.
Yes, I think it's the really interesting part is we can really enlarge the like imagine spaces or the upper bound of the current humanoid robot applications because I think we are not very confident about whether they are useful right now, and we're trying to push the limit and making people more confident about the future of the humanoid robot, and they can be useful for the gaming, for sports, different kind of applications. I think this is a very interesting part that we're trying to like facilitate.
Yeah, very, very cool. Yeah, I guess just to wrap things up, I don't know, like do you guys have any more thing you want to share about the paper? Otherwise,
Yeah, I think we're good.
Okay, cool. Yeah, so I guess usually to wrap up, we want to ask you are there any other papers? Doesn't have to be humanoid, by the way. I mean, it could be any other papers that you come across that you think was pretty cool that you want to give a shout out to. So our viewers can also go and read that paper. I mean, maybe we can invite the authors, to our next episode.
I think we have one paper.
Okay, cool. Has it been published yet?
It's called Humanoid Diffusion Transformer. So. As Chris mentioned, the model is pretty important for the current humanoid control. So currently we are using a paradigm like we are trying to have a motion prediction model, and then we have a RL trained policy to do the tracking policies. And the generalizability is all counts on the RL part. And I think this is the bottleneck for the motion control or the humanoid control tasks. And we have a paper that is about to release called Humanoid Diffusion Controller that's trying to using an offline behavior cloning method for doing the whole body control of the humanoid robot. So in this way, you don't need to train an online policy every time for the humanoid control policy. You can collecting enough expert policies with a paired state and action data. You can collect data from this group, that group, a lot of groups and a lot of works, and using that as an offline sources for learning the humanoid control. I think this will be a more convenient way for improving the capacity, fastness, and generalizability of the future control model, and also improve the expressiveness and scaling capabilities. I think I will release that very soon.
Okay.
And I think there are
sounds
many.
Like sounds like we'll have
yeah.
you soon again. That's very cool. Yeah, I guess it's probably a wrap. Thank you so much for making the time, Siyuan and Yixuan. I think the demos
Thank
are
you
really
for
cool.
inviting us.
It's really cool work.
and thanks for preparing the slides. The slides were I thought very well done as well. Yeah.
By the way, Chris, I'm also a big fan of your account and also your work.
Thank you.
Yeah.
I appreciate it.
I don't know how Chris have all this time to write while doing this podcast while having a regular job.
I don't know.
Anyway, but it's good, man. It's it's definitely.
Yeah, I mean,
good,
I've been
Chris.
following your work for quite a while too. I think it's lots of really cool stuff. Interesting to see you doing humanoids now as well. So
we have done a lot of
the times are changing. Yeah, very cool.
Okay, cool. Then it's a wrap. Then we'll see you next time. All right, Chris, what have you learned?
Yeah, I thought it was really cool stuff about humanoid teleoperation. I think there's a lot of interesting lessons in there for what you can do and how the stuff works. I was really shocked that they managed to get that to work so smoothly with so little data right, and also able to do so many different tasks, whole body control, cool stuff. I don't know. What did you think?
Yeah, it seems that when it comes to just local motion without interaction with very dynamic scene, maybe you don't need really that much data, let's say, to see it. But I think to his point, once you build up a decent teleoperation, whole body teleoperation setup, then you do actually very much want to gather a lot of data in the real world, but do all the interaction stuff, right? Which you
Of
can't.
course.
It's very, very hard to. I mean, you can simulate, of course, but there's definitely benefit to doing it real world teleop. And so I mean, we've I think interview a bunch of these different papers all coming up with.
Okay, so for what it's worth,